Welcome back. This is week 9 of our graduate statistics course. We're going over the bits and pieces that build the ANOVA table because I want you to really understand where the F statistics come from, what's the logic behind it. We've already explained how this piece comes about, right? And that's mapped on to that original figure. Here, that's the total variability in vocabulary score, and then we are computing how much variability is attributed to our explanatory variable and what's left over. And this will be the basis for the computation of the F value. But before, we need to find a way to go from, that's the challenge now, to get from these measures of total variability, total to be explained, total explained, and total not explained, by the explanatory variable in the data set to some average measures of variability. In scaling by a measure that incorporates, so we need to scale by a measure that incorporates sample sizes and number of groups, which are the degrees of freedom. So the degrees of freedom for the group factor is the number of groups minus 1, which in this case, 4 groups minus 1, okay? And then the degrees of freedom for the total variability is the total number of participants minus 1, which makes absolutely total sense, right? Because this is kind of related to the number of deviations that we computed, right? And because we computed deviations from the mean, and the mean should be computed, it pulls 1 degree of freedom out, that's why we subtract from 1. In our live session, I can explain in more detail why we do that subtraction. But it's basically averaging. I computed deviations of 795 scores, so I need to scale that to the number of deviations that I computed, and I just correct by the fact that I already used up and fixed 1 degree of freedom when I computed the mean. That's why I subtract from 1. I'm doing the same for the group. This total deviation came from computing the deviations of each group from the mean. So I computed 4 deviations only. So I need to correct for that, right? I need to correct this by this big value, by a bigger value here, because I used more to sum than here. And the residual will be just 1 minus the other. So to compute the mean square, what I do is just divide the total sums of squares by the degrees of freedom. And this gets me the mean square values, right? So MSG is going to be the total sums of squares, total deviation of group means from the grand mean divided by 3. And this one will be the deviations of the many different individual scores from the grand mean divided by the number of degrees of freedom. So I need these two, because remember, this is the average between groups variability, and that's the average within groups variability, and you want that to be bigger than that. Substantially bigger than that is necessary for us to say that the means are playing an important role in this data set. Now, the F ratio is simply the mean square deviations for the groups, the mean square deviations of group means from the grand mean, divided by the mean square deviations that are unexplained by the group means. So if you look here, the F ratio is simply this one divided by that. Between groups variability, within groups variability. Variability that's nothing to do with you being in different groups. And you get to an F ratio of 21.73. Then what do? We look at the distribution, and that has 2 parameters, the degrees of freedom of the group and the degrees of freedom of the error, the within group variability, which is 3 and 791. Where did I get that? 3, number of groups minus 1. And this here is the degrees of freedom total, which is the number of participants minus 1 minus class, so I get to this. So I create my F distribution based on these 2 degrees of freedom, and here's the 21. This is my F ratio. Imagine it's right at the tail. You almost get 0 probability of getting that. So that's our sampling distribution under the null hypothesis. And what's the probability of us getting this particular value given these degrees of freedom? And lower tail is false because we want upper tail. We don't want them to get anything on this side. The probability is 0.0000, 12 zeros, 1. So it's pretty close to 0. The probability of seeing that much more between group variability than within group variability is very, very unlikely under the null hypothesis. That F basically equals to 1. P-value is the probability of at least as large a ratio between and within group variabilities if in fact the means of all groups are equal. So saying this easily, it's the probability of observing at least an F ratio as high as this under the hypothesis that all groups are just the same. The area under the F curve with degrees of freedom DFG and DFE above, these degrees of freedom is, so the p-value is the area under the curve that goes above this particular value, right? It's the tiny little tail above that value because it's the probability of getting an F ratio that is this magnitude or larger, okay? So that probability is less than 0.0001. It's virtually 0. So what do we do with the null hypothesis? If p-value is small, less than whatever alpha level you established, again, traditionally we establish that at 0.05, we reject the null hypothesis. And we say that the data provide convincing evidence that at least one pair of population means are different from each other. But we cannot tell which one. Because remember, the null hypothesis is that all of them are equal. The alternative is that at least 2 means are different from each other. At least 2 are deviating a lot from the grand mean, let's say. So, if p-value is large, we fail to reject the null hypothesis. Large meaning greater than 0.05 by convention. The data, if that's the case, the data do not provide convincing evidence that at least one pair of population means are different from each other. The observed differences in sample means are attributable to sampling variability or just chance. Okay? So if p-value is small, we say we're rejecting the null hypothesis that every single mean is exactly the same or the difference is just due to random variability. We say there's something going on, but this something is that at least 2 means are different from each other. We don't know which ones. If we fail to reject, we assume that any variation between means or any variation of the group means from the grand mean would be expected are very typical to be seen under chance alone. Yes? And this is the case in this particular data set that we're working on as an example, because p-value is really, really, really tiny and small. Now, which means differ is the next step. We do follow-up analysis for that. To find out, we need to run different tests for each possible pair of groups. So why didn't we just do that to begin with, if that's what we will end up doing? Because running multiple comparisons with probability of error of 0.05 leads to a higher error rate for the experiment as a whole. So every time you run a comparison, now you have, the first one you have, 0.05 only of observing that particular F statistic or that particular T, let's say. It's very low, the probability of observing that under chance conditions. But it can happen. There is a 5% chance that you're mistakenly rejecting the null hypothesis. Now you run a second test. Now instead of just having 5% probability, now you have 10. Now you run a third test. Now the probability of you making an error, experiment-wise error, is 0.05 times 3, so on and so forth. So instead of beginning with these multiple testing, we run the ANOVA test to get permission, so to speak, to explore which pairs are different. Because the ANOVA tells with one test only, and then with 0.05% chance of error, whether at least two means are different. So this provides us with some confidence to then look and explore, because we already done our job at determining that at least two are different, so it makes sense to look. So there are different strategies for pairwise comparison that differ in how they control for experiment-wide error. The first option, well, maybe we should stop here and come back in the next video and explore all of the options on one video. That makes sense. It's a good time for a break. So we'll take a break and then we come back and we will address the step-by-step of the follow-up analysis. See you then. Bye-bye.